So in this section, in special electrical machines, we are going to see the self-control of permanent magnet synchronous motor. So here, as the speed increases, armature supply frequencies will also change proportionally, so that the armature field always move at the same speed as the rotor. The armature and rotor field move in synchronism for all operating points. Here, accurate tracking of speed by frequency is realized with the help of rotor position sensor. When the rotor makes certain predetermined angle with the axis of the armature faces, the firing pulses to the converter feeding the motor will also change. The switches are fired at a frequency proportional to the motor speed, thus the frequency of the voltage induced in the armature is proportional to the speed. Here the self-control of PMSM is shown in the slide. So at high power levels, the most common power converter configuration is the current fed DC link converter. The phase control thyristor rectifier on the supply side of the DC link has the current regulating loop and operate as a controlled current source. The regulated DC current is delivered to the DC link inductor to the thyristor of load commutator inverter, which supplies the line current to the synchronous motor. The inverter gating signals are under the control of shaft position sensor, giving a commutatorless DC motor with armature current controlled. The thyristor of these inverters utilize load commutation because of the generated EMF appearing at the armature. It is ensured by the over-excitation of synchronous motor so that it operates at leading power factor. Hence, it reduces commutating circuitry, low losses, and is applicable to power levels of several megawatts. The shaft position is sensed by the position sensor. The shaft speed is obtained by converting the position information. This speed is compared with the reference speed signal, which provides the speed error. This is the current reference signal for the linear current loop. This reference current is compared with the sensed DC link current, which provides control signal for the rectifier thyristor. The sensed shaft position is used as gating signal for inverter thyristor. Com commutation at low speed, low commutation is ensured only at high speeds, whereas at low speeds the EMF generated is not sufficient for load commutation. The inverter can be commutated by supplying pulsating on-off DC link current. This technique provides large pulsating torque, but this is not suitable for drives which require smooth torque at low speed. The DC link current is pulsed by phase shifting the gate signal of the supply side converter from rectification to inversion and back again. When the current is zero, the motor side converter is switched to a new conduction period and supply side converter is then turned on. Time required for the motor current to fall to zero can be significantly shortened by placing a shunt thyristor in parallel with a DC link inductor. When the current zero is needed, the line side converter is phased back to inversion and the auxiliary thyristor is gated.